In this video, we'll examine the concept of independent events in the world of probability. And we'll return to an example we looked at previously when we talked about conditional probability. And that is one in which we roll a pair of dice, and we're going to define one event, A, to be that the first die shows a 3, and the second event, B, to be that the sum is 6. And off to the right here, I have a little piece of the sample space that shows us the outcomes that are involved with these two different events. And I'm going to calculate two probabilities to sort of start us off. One is going to be the probability that event A occurs. That is the probability that the first die shows a 3. There are 6 outcomes out of the 36 equally likely outcomes that involve that event, so this probability is going to be 6/36 or 1/6. And then I'm going to calculate a conditional probability, the probability of A given B. And you'll need to recall that if we're assuming that B has occurred, then we're limiting ourselves to only those 5 outcomes that involve B, not the entire 36 in the sample space. And of those 5 outcomes, only one involves also A occurring. And so we're in a situation where these values are different. The unconditional probability, the probability of A, if we don't know anything about the sum, is 1/6. But the minute we know that this sum is 6, now our estimate of the probability of A changes. The probability of A given that condition is 1/5. So there's something going on between A and B. There's a situation in which information about B changes our expectations about A. And we won't work it out in this video, but it's fairly easy to show that that means that information about A changes our expectations about B. This is going to be a pretty important concept for us moving forward, and so we're going to give it a name. We're going to call it independence. So we'll make the definition if the probability of A given B is equal to the unconditional probability of A, then we'll say events A and B are independent. If this condition is not met, then we'll say they're dependent. And so in the case of our example, the values are not equal, and so there's some sort of dependent relationship going on between A and B. You can rearrange this. I should box this up because this is a pretty important definition. You can rearrange this condition algebraically by making use of some things that we know. The probability of A given B is the probability of A intersect B divided by the probability of B. And what we're saying is that would have to be equal to the probability of A. Now if I just multiply through here, this says that the probability of A intersect B is equal to the probability of A times the probability of B. And so this is a separate condition that you can use to check whether two events A and B are independent. So we'll make a little theorem that says something like this. If probability of A intersect B equals probability of A times probability of B, then A and B are independent. And that's true only if they are independent. So we have two separate ways of checking for whether two events are independent. We can find the unconditional probability of one of them and compare it to the conditional probability of one given the other. If those numbers are equal, the events are independent. If not, the events are dependent. Or we can calculate the two separate probabilities and the probability of the intersection, and if this condition is satisfied, then the events are independent. Otherwise, they are not. Here is an example of a situation that we might want to test to see if there's an independent or a dependent relationship between a couple of events. So we've got a group of probability and stat students, 39 of them make and use complete sets of flashcards for the third test of the course that they're in, and 8 don't. Following the test, 35 students are satisfied with the grade that they earned, and 30 of those 35 had made and used flashcards. And so the first item of business is to organize the information into a contingency table And the second item of business is to determine whether making flashcards and being satisfied with your result are dependent or independent. A couple of ways we can organize this. I'm just going to say along this dimension here, people are either satisfied or not satisfied. And then along the other dimension, they either made cards or they didn't. And then we'll plunk in the values that we have and start working on the independence question. So there are 39 students who make and use flashcards, and there are 8 who don't, which must mean there are 47 students in total. 35 students are satisfied with the grade that they earned, and 30 of those had made and used flashcards. And with this information, it's fairly easy to fill in all the rest of the values just by making sure that the numbers on the interior add up to the appropriate marginal total. So that's got to be 3, and that's got to be 12, and I can check that those add up to 47, and in fact they do. So now, there are a couple of different ways that we can check for independence. One is to compare a conditional probability to an unconditional probability. So we could ask, for example, what's the probability that somebody was satisfied with their result, and compare it to the probability that they were satisfied given that they had made flashcards. And if these numbers are equal, then these events are independent, and if not, then they are not. So the probability that somebody was satisfied is 35 out of the 47. And the probability that somebody was satisfied given that they had made cards is 30 out of 39. And then the question is, how close are these? If you do the calculations, you find that the probability that somebody's satisfied with their result is 0.74. The probability that they're satisfied given that they made cards is 0.77. And so what do we think about that? If we're being strict about it, then we would say that these events are dependent, that making flashcards slightly increase the probability that you would be satisfied as opposed to the unconditional probability. But if we're reasonable about it, we might look at this and say, nah, they're pretty close. You know, if they're dependent, they're not strongly dependent. And one of the things that we hope to do before the end of the course is to be able to find some more sophisticated ways of parsing that out and seeing if we can make a conclusion in these kind of borderline situations. Another thing that we can do to check, sort of an independent, separate method, is to take a look at the probability people are satisfied, the probability that they made cards, and then take that product and compare it to the probability of the intersection of those two events, which was the thing we were discussing a few moments ago. Probability that you're satisfied and you made cards. So the probability you're satisfied is 35 out of 47. The probability you made cards is 39 out of 47. So the product of those two probabilities is 35 47ths times 39 47ths. And I worked this out ahead of time. It comes out to about 0.618. The probability you're satisfied and you made cards is 30 out of 47, which it turns out is about 0.638. And maybe unsurprisingly, we're in this sort of borderline territory again where, yeah, these are not strictly equal, but they're close, and so if there's some kind of dependence, it's not a particularly strong dependence. But this at least is a good situation in which we can show the two different methods of assessing whether two events are dependent or independent.